Hi, my name is Wolf, and this is my entry for the Mega Fave Number playlist created by James Grimes. It all started a few years ago when I read on Wikipedia that the ampere was being redefined. The ampere is the fundamental unit of electric current equal to 1 Coulomb per second. Personally, I think that instead of having the ampere be the fundamental unit, it should be the Coulomb, since that's more closely tied to a physical constant. But that's just me. So from 1881 until 2019, the ampere was defined as that constant current which, if maintained in two straight parallel conductors of infinite length of negligible circular cross-section and placed 1 meter apart in vacuum, would produce between these conductors a force equal to 2 times 10 to the negative 7th newtons per meter of length. In other words, if you take two metal rods that are infinitely long, place them in an infinitely long vacuum chamber, position them 1 meter apart, and run current through them until they repel each other with 1 newton of force for every 5,000 kilometers of length, then the amount of current you're running through them is 1 ampere. This definition was nice because it meant that the magnetic constant mu0, also known as the permeability of free space, was equal to exactly 4 pi times 10 to the negative 7th henries per meter. However, as time went on and electrical measurements became more and more delicate, scientists decided they needed a more precise definition for the ampere, preferably one based on something that could actually be measured without using infinitely long metal rods. They needed a physical constant. They needed the elementary charge. The elementary charge is the electrical charge of 1 proton, or the opposite of the charge of 1 electron. Since all matter is made of these particles, along with neutrons, which have no charge at all objects must have a charge that is an integer multiple of this value, or a third of it if you count quarks. Indeed, this was one of the first indicators that there was an elementary charge, a quantum value, the smallest charge that an object could have, and by which all charged objects could be evenly divided. So for 138 years, the elementary charge was subject to experimentation, and was determined to have a value of about 1.6021766,209 times 10 to the negative 19th coulombs. Subsequent experiments would add a few more digits to this figure, which were then put in parentheses for some reason. Anyway, in 2018, the International System of Quantities decided that rather than assign an exact value to the magnetic constant and use it to derive the elementary charge, they would assign a value to the elementary charge and use it to derive the magnetic constant. So, as of the 1st of May 2019, the elementary charge is equal to exactly 1.602176634 times 10 to the negative 19th coulombs. It's similar to how the speed of light is now exactly 299,792,458 meters per second, after the meter was defined as the distance traveled by light in 299,792,458th of a second. This is where I began to notice a problem. The elementary charge is written in scientific notation, but since it's exact, we can convert it to a fraction. Instead of multiplying it by 10 to the negative 19th, we can divide it by 10 quintillion. Then we can do some fraction manipulation and move the decimal point 9 places to the right while adding 9 zeros to the denominator. We can try factoring it, but we only get a 2 out of it. Finally, we flip everything upside down so that rather than the number of coulombs in an elementary charge, we're seeing the number of charges in a coulomb. We can then convert this to a proper fraction and see that 1 coulomb is equal to 6,241,509,74,460,762,607 and 621,837,581 801,088,317 elementary charges. See the problem here? This number isn't an integer. By choosing this definition of the Coulomb, the ISQ set it to a charge that no object can ever have. This seemed to me less than ideal, so I decided to try and find a better value for the ampere. The current definition is only a few years old, so maybe if we can find a new one, the international community will be open to the change. So from 1881 to 2019, the elementary charge had this value, giving the Coulomb this value. Then in 2019, it was defined as having this value, giving the Coulomb this value. This means that the Coulomb has already changed by over 50 billion elementary charges. This is a tiny charge. For comparison, the static charge in your car right now is probably about 100 times that difference. However, if the ISQ is willing to deviate that far in either direction, it shouldn't be that hard to find an integer value for the Coulomb based on the elementary charge. So what we need to do is find a number somewhere in this general vicinity. The first thing to ask is, are there any other special properties we want this number to have? Having it be prime would be cool, but the whole point of this is that we want the Coulomb to be an integer multiple of the elementary charge. It would probably be impractical if it couldn't be evenly divided by anything else. In fact, what we really want to do is the opposite. We want to find a number in that range with as many factors as possible. Here we can stand on the shoulders of another YouTuber from this challenge who submitted his mega-fave number, 720,720. 720,720 is the smallest integer that is divisible by every number up to 16. Floor dividing by this number gives us 8,660,102,500,916. Now the first thing I noticed about this number are those two zeros near the end. If we subtract 916, we get a nice round number with 5 zeros at the end, without substantially deviating the value. Of course, we could also add 84 to deviate the number even less and still get 3 zeros, but after we divide by 1,000, we're left with 8,660,102,501, which is prime. So I'm going to stick with the 5 zeros number. After we multiply it by 720,720, we get 6,241,509,073,800,000,000. And this is my mega-fave number. As you can see, it's relatively close to the SI value. It's got plenty of factors, including every integer up to 16, every even number up to 32, most composite numbers up to 100, at least one number in every 10 up to 400, all powers of 2 up to 512, all powers of 5 up to 390,625, and all powers of 10 up to 100 million. And if this isn't enough for you, it's pan-digital. That's right, if you ignore the zeros, every digit from 1 to 9 appears exactly once in this number. Oh, and if you don't ignore the zeros, there are 10 of them in total, as many as the base that it's in. And 8 of them occur after the significant digits, the same as the last significant digit. So that's my favorite number greater than 1 million. I hope you enjoyed this video, and I hope that if you ever have to measure the electric charge of something, you'll use a charge that can actually exist.